Did we do bond order on Monday? Okay. I think we stopped here, right? All right. Okay, so we just introduced a bunch of stuff with molecular orbital theory on Monday, okay? We talked about that in terms of hybridization, and we talked about bonding and anti-bonding orbitals. If you remember here, sigma and pi bonds, and then sigma star and pi star. Whenever you see that star, that's how you know it's anti-bonding. The other thing we talked about was destructive interference and constructive interference. And we talked about how if you can think of electrons in terms of a wave, you're going to get the, if they're in sync, you're going to get constructive, and that's where you're going to find the electrons being shared between the two nuclei. When the destructive interference occurs, meaning if you're thinking of the electrons in terms of a wave, you know, they're out of sync. One's up, one's starting up, and the other one is starting down. You get this separation. So the electrons are found on the outside of the nucleus. So when we talk about the electrons as far as stabilizing, it's much easier for these electrons to first go to the lower energy orbitals, and only going to the higher energy orbitals as they're kind of forced to go there because there's nowhere else to go. That's going to require energy in. The lower ones, they can just drop down to those lower orbitals. So anti-bonding molecular orbitals are you're destabilizing, they're higher energy, and the electrons have to be kind of forced into those higher energy positions for some reason or another. Or bonding are you're stabilizing, lower energy, much easier. It's easier to climb down a mountain than it is to climb up a mountain. okay? So bond order is the relationship between the bonding and the anti-bonding orbitals. Basically, what's in the bonding and what's in the anti-bonding. So your very simple equation to figure out bond order is going to be number of bonding electrons minus the anti-bonding, whole thing divided by 2. Okay, so bonding minus anti-bonding divided by 2. When we talk about paired and unpaired electrons, we talk about paramagnetic and diamagnetic. Excuse me. Something that is diamagnetic has all pairs. There's no single electron in an orbital. It's all paired up. You can remember that by the word dia meaning 2. All the pairs are present. A paramagnetic means in one or more of the orbitals, there's only a single electron. Okay? So, having said that, let's look at some examples of how we're going to set this up. So while I'm getting set up, go ahead and take a minute. Hold on, let me. Go ahead and take a minute and right. That's as far as it'll let me zoom. Okay, that stinks. Okay, go ahead and write all this down, and then we'll write this down, and then we're going to have to write this down. I guess I just left too much room between it. Let me know when you're ready for me to scoot it up a little bit. You guys see that okay? Because it looks really small on my screen. If you have colored pencils or a different color ink, today is a good day to use it. Doesn't matter what color, just contrasting from whatever color you're writing in right now. If not, use a highlighter. Like use whatever pen you have and then use a highlighter. Because I'm going to use this same scheme to compare 2 different H2s. Okay. And honestly, it's just a good idea to bring in different colored stuff into this class every day anyway, because there's going to be lots of times that we're going to use alternating colors on one example. All right, everybody got this written down? Or are you still working on it? Got it? Okay. All right, so we're going to do H2 first. All right, now H2 literally is just one hydrogen bonded to another hydrogen. Okay, we're going to differentiate which hydrogen we're talking about by using these subscripts A and B. Okay, now if you remember, hydrogen is a diatom, and we're actually going to be doing a few of the diatoms. Remember, the diatoms make the shape of a 7 on the periodic table, and don't forget hydrogen. There are 7 of them, right? N2, O2, F2, Cl2, I2, Br2, and don't forget hydrogen. All right, now, this side here are the contributing valence electrons from hydrogen A. This side here are the contributing valence electrons from hydrogen B. Down here is going to be your bonding molecular orbital, and up here you can see it's sigma 1s star. This is going to be your antibonding. Anytime you see the star, that's how you know it's antibonding. Okay? All right, so like we said before, it's easier for these electrons to drop down into a lower energy orbital. So to form this orbital here from these 2 electrons, one of them is going to contribute its electrons, and the other is going to contribute its electron. Okay? So what we get is both single electrons are used up, okay? And they're put into this lower orbital. There are none left to use to go up into this anti-bonding higher energy molecular orbital. Okay, so the bond order is the bonding minus the anti-bonding. I know you can't see it, but you should have written it down, divided by 2. So we have 1, 2 that are bonding. We have 0 that are anti-bonding, divided by 2. So 2 minus 0 is 2. 2 divided by 2 is 1. The bond order for this is 1. Okay. Now, would this H2 be paramagnetic or diamagnetic? What do we say those meant? Dia means 2, so what does that mean? That's how you remember it. Really, nothing? 2 what? Apples? What are we talking about here? What's the whole entire point of this? What is the focus? I mean, is it the neutrons? Electrons, okay? So if we're focusing on the electrons, and I'm talking about dia meaning 2, the electrons do what? What do we call it when there's 2 of them together? Starts with a P. What do you think? How about pair up? Okay, when they're diamagnetic, we have 2 electrons, they're in a pair. There's no single ones here. So it's paramagnetic. I just said paramagnetic, I meant to say diamagnetic. Dia, because it's a pair. There are no single electrons in an orbital. Okay? All right, now, I want to compare this to H2 minus. If I have H2 minus, that means I have gained or lost an electron. Gained. There's an extra electron there. So we'll just say, for sake of argument, that it's going to be HA has that second contributing electron. It doesn't matter which hydrogen has the extra one. I'm just picking A because I feel like it. Okay? So now what's going to happen? We're still going to have one contribute down here, one contribute down here to make this pair again. Remember, we're in F, so only 2 electrons can be there. But now I have one left over. Where is it going to go? To the top. The only place it's got to go. The only place it's got to go is to the top. So now the bond order has changed. The bond order goes from 1 to 1/2. Okay. Now, bond orders, generally speaking, tell you how many bonds are present. So a bond order of 1 is a single bond, a bond order of 2, double bond, bond order of 3, triple bond. The higher the bond order, the more stable the bond is. Okay, so when I look at this, I go from being pretty stable diamagnetic to now less stable paramagnetic. Okay, it's paramagnetic because there's one that doesn't have a pair. Okay? All right, questions about this? If you don't understand this one, now's the time to ask because this is the simplest one that we're going to do. This is like kind of like the basics of it. Okay, we're good? All right, can I go to the next example? All right, so the next one we're going to do is N2. And by the way, I think it starts with carbon, maybe, in your book. I'm pretty sure it starts with carbon in your book, where it shows you the molecular orbitals for carbon all the way through to F2. So I just picked hydrogen, and then I picked nitrogen, and the other one we're going to do is oxygen, because nitrogen and oxygen are going to do a flip-flop. So just copy all this down. And again, we're still doing the Na and Nb, just to differentiate between the two. Also, take out your periodic tables when you're done writing this down, or pull one up on your device. In case you missed it, there's All right, so just like the hydrogen, we're going to differentiate nitrogen, subscript A on the right. These are the contributing valence electrons, and B on the, I said right, on the left, and B on the right. Okay, now, if you look at where nitrogen is, on your periodic table, you can see that nitrogen's valence electrons is, first of all, nitrogen is in group 15, so it has 5 valence electrons. 2 of them are coming from your s orbital. So this is why we start with 2s, because it's in the second row. And then the other 3 are coming from the p orbitals in the second row, which you can see as we go across the periodic table. Okay? All right, so what's going to happen is the same thing that happened with hydrogen. In the s orbital, there can only be 2, but there are 4 valence electrons total. So 2 are going to go down, 1 from that nitrogen, 1 from that nitrogen, and the other 2 are going to go up. Okay. So now all of our s valence electrons are taken care of. Now we're going to jump up to the p. You'll notice here, and this is where the difference comes in with oxygen, pi 2p goes first, and then sigma 2p goes second. In oxygen, these are flip-flopped. That's because oxygen is more attractive to the sigma rather than the pi. Okay? So I got 3 electrons, and this is 2p. How many electrons can a p orbital hold? 6. So I got 1, 2, 3, 4, 5, 6. These are all going to go in here. Okay? Why didn't I put 6 in here? In just the bonding one. What do you think? What about this up here? That's another pi, right? It's another pi. Okay, so I got 1, 2, 3, 4. They're not going to jump up to this pi because there's something more stable right here. Okay? Okay? All right, so let's talk about bond order. It's going to be bonding, so 2, 4, 6, 8, minus our anti-bonding, divided by 2. So 6 divided by 2, it's a bond order of 3. What does that tell us about the bond between the 2 nitrogens? What does our bond order tell us about the bond, generally speaking? It's stable, right? The higher the bond order, the more stable it is. How many bonds will be present between those 2 nitrogens based on bond order? Well, we said with hydrogen, a bond order of 1 means that there's 1 single bond. What does a bond order of 2 mean? double bond. So we should expect that nitrogen has a triple bond. Let's test it, shall we? Okay, I got a total of 2, 4, 6, 8, 10 valence electrons. Okay, so 10 valence electrons divided by 2, that's going to be 5 pair that is available to us. Okay, so here's nitrogen A, nitrogen B. Normally we say the most electronegative gets first dibs. In this case, they're exactly the same thing. So we're just going to kind of pick one. Okay. 1, 2, 3, 4, 5. Not each nitrogen has an octet. So we can borrow. So now it would be still don't have an octet, right? So we can borrow again. Lo and behold, nitrogen N2 has a triple bond, just based on the Lewis structure. That will be its final structure. So we could predict, based on the bond order, how many bonds would be between the two nitrogens. Okay? All right. Now we're doing oxygen. O2. Note the flip. Fluorine will have that flip also. All right, I want you guys to see if you can figure this out, your molecular orbital diagram, and also the bond order. All right. Let's see if you got it. You get it? It should not pair in one box. Why do you think that might be? I put one in one box, one in the other. Why did I not pair them? Think about electron configuration. Think about the exceptions to our electron configuration. We took from the S, right? Borrowed from the S and put it up to the D. Why did we do that? In fact, when I drew it, why did I go 1, 1, 1, and then go back and double up? Easy how? What do you mean?
I said even.
Oh, even? Yes, even, but why does even matter?
It's more stable
Why? You're correct. Why though?
to have a full orbit.
It is more stable. Stability drives everything in here. So it is more stable to have one in each orbital rather than a paired one with an empty orbital. It is to have to be even is more stable. It is more stable because it would rather, even in this higher energy thing, and especially in the higher energy ones, it would rather have one in each than a pair and an empty. Stability drives everything, okay? So for our bond order, 2, 4, 6, 8 minus 2, 4 divided by 2 bond order of 2. How many bonds should it have between the two oxygens? 2. Okay. Now, is this paramagnetic or diamagnetic? Diamagnetic. Dia meaning 2, 2 what? Not bonds. Sorry. 2 pairs, right? Is every single electron in here paired up? Nope. So we are dealing with paramagnetic. These are not paired, so it's paramagnetic. In your textbook, where it has all these examples, there's several pages of them. I don't remember the page numbers, but this is in chapter 6. At the end of all these diagrams are 2 example exercises. I highly recommend you understand them. You might see them somewhere, like on a test, okay? And it walks you through every step of those 2 examples, and especially the now you try portion of it, where it gives you the thing you have to answer, and then it says, you know, all the explanation, the summary, the strategy, all that. Then at the very bottom, it's like, okay, now try this one. I like those. I'm just saying, you might see them. Okay. All right, questions about this? No, nothing? Everybody's getting 100? All right, perfect. That is all on molecular orbitals that we're doing today. Okay, let me pull this up. Once we do chapter 7, I'm not starting chapter 7 today. Once we do chapter 7, it's all our reactions and types of reactions. After chapter 7, you will have your next test. So we're going to start reactions on Friday, and we'll probably finish it up by Wednesday of next week, assuming everything goes perfectly the way I anticipate it. And then you will have an online test for this, because I don't want to use another class day for it. It's going to be done through Respondus, which is a lockdown browser. I will send out instructions and the announcements on how to do that. And we'll go from there. Okay. And it'll probably be, I'll probably give it I'll keep it open for 2 days, but once you start it, you can't stop. So you can pick whenever you want to start it over those 2 days, but once you start, you can't stop. Now let's do just a quick show of hands. For you guys, who would prefer it to do it over a Friday and have it open all day Friday and Saturday versus all day, say Sunday and Monday? So Friday and Saturday first.
Either one for me.
Either. So if you don't care, just raise your hand. If you have no opinion, really? Okay, so okay, you didn't raise your hand at all, do you? Do you have stuff? You don't care?
Mondays.
Huh?
I'd rather take on Mondays.
You'd rather take it on Monday? All right, so maybe what I'll do is I'll just keep it open from Friday to Monday. And then y'all can check. But again, once you start, you can't stop. Okay? It will be timed, et cetera, et cetera. Yes?
We have all the periodic table and stuff like that.
When I email you the directions, I'll tell you what's on the test, how many questions, what you're allowed to use, all that kind of stuff. Okay? All right, any other questions? All righty. Have a good day.